1 and 10-2. I've asked you guys to work on the problems up to 48. Let's take a few minutes and field some questions, as there might be some at this point. Aiden?
You do 21.
21? Sure. So 21. So the first thing that we want to do is to eliminate the parameter. Doesn't really matter on this one which one you start with. Let's just say for the sake of argument, though, we start with the x. So I'll add 1 to both sides. We'll multiply by -2. And then square root both sides. Now, I'm not going to worry that there's a negative sign underneath the radical here. Why not? Because there's a variable under there too, right? If x is like -5, then it's no big deal, right? So, woof. Yeah, I know. Totally freaked me out too. All right. Well, now that we have this, we can just plug this in for the there. Oops, and we probably have a plus or minus here, right? Because we square root both sides. Right? That feel okay? Fraction cleared. The domain is coming from the x coordinate. And my interval, or the parameter, is over all real numbers. So what I care about here, since this is a quadratic, is the vertex and then the endpoints. Now, here it's easy to see that because this is a parabola that's opening down, since the leading coefficient is negative, that both endpoints are going to be going to negative infinity. The vertex then is the part that I'm going to care about. To find the t coordinate for that vertex, that's going to be -b over 2a. And then when I do x of 0, I get -1. So my domain goes from, negative infinity up to -1. And then the range, since the y-coordinate is a linear function and the domain is all real numbers, I know that the output for that function is also going to be all real numbers, without really having to do anything there. Is that okay, Aiden?
On the answer key, it says the answer is y is equal to plus or minus the square root of -8x minus 8.
Sure, which is the same thing we have here. So if I take, you said the square root, you had some others, but 8x minus 8, right, was the part that's underneath that's different. So if I factor off of 4, you can do like that. What, you get it. Or 8 minus 8x or something. Yeah, it's the same thing. It's just rearranged. No big deal. Either answer would be fine with me. Yeah. Jack, so your hand?
Yeah, can you do 40, please?
40? Sure. So we remember that for a unit circle that we had x of t was cosine t and y of t was sine t, right? Now a unit circle has radius 1 and center at 0, 0. Everybody agree with that? So if I then multiply each of the x coefficients by, in this case, square root of 11. That'll stretch out vertically. The biggest x coordinate now goes to square root 11. So like the distance, the biggest distance from 0, 0 horizontally would be square root of 11, right? And if I do the same thing to the y coordinate, now the y coordinates get multiplied by square root of 11. So I now have a circle still, but its radius has been changed to square root of 11. Does that feel cool? Then I have to worry about the center. If I add 4 to every x coordinate, it's going to shift the entire circle over to the right 4 units. And then if I subtract 3 from every y coordinate, it's going to shift the whole circle down 3 units. So we're now at a circle with center 4, negative 3, and radius square root of 11. Does that feel okay?
Yeah. Oh, yeah.
And that's the gist of it,
Yeah.
right? Does that make sense?
Yeah.
No problem. Soph, I thought I saw your hand at one point. 25? Sure. So, sorry, Jack, we need to put an interval here on this. Anything that's bigger than, or anything that's longer than 2 pi will work. 1 to 8, 0 to 1,000, or just 0 to 2 pi minimally, like whatever.
Thank you.
Yep. And then you said 25, Soph? Okay. So this is the one where you're not going to do this directly. Hopefully you recognize that sine and cosine is a circle, right? So this circle should have radius, well, not the one that we've drawn. It should have radius 4. For this equation, because the 4 is sitting out front there. So really, when I do this, I have x squared plus y squared should equal 4 squared. To just kind of confirm that, we could plug in and just check to make sure that this does indeed give us 4 squared. Now notice that even though one of the coefficients was positive and the other one was negative, that makes no never mind to us. Because when we plug this in and do the squaring, the negative sign gets eaten up while we do the squaring. You know what I mean? So for sure, that's my piece. And my domain here for a circle whose radius is 4, centered at the origin, is just negative 4 to positive 4, and the same thing with the range, right? Is that okay? So these ones that are circles or whatever, have the sines and cosines, you can approach it differently than we did the previous ones. And you can imagine that these kinds of eliminate the parameter problems could become really difficult if you have like stuff that's mixed with sines and cosines or whatever in there, or like linear function and a trigonometric function or something. Those could become really difficult kinds of problems. We won't see that in this class, but they don't always have to be like really convenient like they have been for us. Anybody else questions from these problems? Okie dokie. That's cool with me. So today we're going to do section 10.3, where we're going to start talking about polar functions. But before we can talk about polar functions, we really have to introduce the idea and define the polar coordinate system. So up until this point, all the graphing we've done in any math class has been on the Cartesian coordinate system, where we're plotting x and y's. Even in the previous sections where we dealt with parametric functions, which were different than Cartesian functions, we still graphed them the same way, right? We're still just graphing x's and y's. Everybody's okay with that? Today, though, we're going to define a new coordinate system called the polar coordinate system. I'm just going to abbreviate that as PCS because we're probably going to write that a bunch of times, and polar coordinate system's a whole heck of a lot of letters, and I'm just not about that life, you know. All right. Okay, so we say a point in the polar coordinate system is defined in general by r comma theta, where r is the distance from that point to the origin, and theta is the measure of the standard form angle whose terminal side intersects that point. Now, you might have noticed inside the content library, I have a file called Polar Graph Paper. I've included that here. I'm dropping it in to our notes right now because I'm going to do all of these examples and talk about polar coordinate system using this Polar Graph Paper. It's there for you guys to use if you need it in your homework. As many times as you need to kind of include it, right? You'll probably need more than one sheet of it. You know what I mean? Okay. So if I look at this polar coordinate system, this is not a spider web. It's not a bullseye, okay? Even though it kind of looks like those things. So each of these concentric circles is representing a different value of r. So like the first circle is when r is 1, then r is 2, and then 3, and then 4. And I guess this one over here is 5, 6, 7, and that last one out there is 8. Everybody okay with that? When we say concentric circles, what do we mean? Good, circles with the same center, right? In this case, that center is the origin at 0, 0. Hi, Michelle. Forgot the schedule changed? Yeah. Take a picture of the schedule before you leave so you don't do the same thing next time. You know what I mean? Yeah. Cool. All right. Everybody's good with that? the straight lines are representing the angles. So the straight lines are all in 30-degree sections, or pi over 6 radians. Nope. Nope. Yeah, that's right. Okay. So we have 2/6 and 60 degrees. 3/6 or pi over 2. I'm going to stop writing the degrees here the whole time through because it just gets a little clustered and like you guys can count by 30s. That's okay. All right. So then we have 4 pi over 6. And then we have 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, and then 11 pi over 6, and then back here to 0 or 2 pi. Is everybody cool with how to kind of read the polar graph or the polar coordinate system, the polar graph paper that I've included here? All right, so let's graph some points in polar coordinate system, right? That's the starting point. So let's say we want to graph 3, 120 degrees. When I do this, I like to start with the angle. So we got 30, 60, 90, 120 is here. And then I'm counting 3 out from that. So 1, 2, 3. Maybe we'll do 1, 2, 3. So there's our point. Everybody happy with that? No big deal. Let's go over here and try this one. So here we have -2 pi over 3. So we'll start by writing this in. So we have pi over 6, and then here's pi over 3. So we're on this piece here. Okay, but now I have -2. What the heck do we do with the negative? All it means is that we're just like flipping the angle line we're using. So we're just going to be over here now. And then we're just taking 2 units down then. Is that cool? Anybody make an observation right here? Tanner? Right. So what does that kind of imply then? Yeah, that's absolutely the point. Yeah, go ahead. Yeah, so there's going to be multiple ways to name the same point, right? As I just keep wanting to call you Ian, and that's not the right name. That's not the right name. I'm a failure. Yeah, go ahead. Evan. Jesus. Took me a while to get there. I don't know why that got stuck in there. It's like the first time I've done that. Yeah. Anyways. Yeah, so there's more than one way to name a point, right? We called this 4 pi over 3, or we can call it -2 and pi over 3. Both of those are describing the same location. And in fact, there's not just 2 ways to name that point. Could there be more than 2? How else could you have named it?
like coterminal angles.
Yeah, I could use coterminal angles. So if I did 2 and 7 pi over 3, or negative 2 and 7 pi over 3, where I've added 2 pi, that would be the same location. And I could add 2 pi to that, and 2 pi to that, and keep on going and generate how many? Infinitely many ways to describe any location here. Okay? Very cool. Good job. Let's do one more example, and then we'll kind of formalize that notion that we just observed. So, what if we want to graph negative 1, negative 100? Well, again, I like to start with the angle, but I'm not going to graph negative 100. I just find the positive angle coterminal to that because it's a little bit easier to deal with. You could go backwards, I suppose, but like, I'll pass on that. I'd rather just worry about stuff between 0 and 360. So 260 is what, right about there-ish, probably? Now, because it's negative, what do we have to do? And we have to flip it across. And then we're just taking the first point. Is that cool with you guys? So the negative angle doesn't do any flipping, right? The negative angle is just a negative angle. The flipping only comes when the radius is negative. Or the r is negative, I guess I should say. We didn't call it the radius, but like, it's when we have the circles drawn in there, it's like I can't help but calling it a radius because it's the radius of a circle. Okay. So let's formalize that observation we just made a moment ago about there being infinitely many ways to describe a location in the polar coordinate system. Right? So let's do that. All right. So given some point P in the polar coordinate system, any point that coincides with P must be of the form. So coincides to a point just means we're describing the same location, right? Coincides means they're overlapping. If it's just a point, the only way they overlap is they occupy the exact same location, right? Okay. So we have the things that are coterminal to it, or the things that are the same point, or the same radius, but the angle is coterminal, right? Or we have the things where the radius is the opposite sign. We flipped it across and worried about the things coterminal to it. And then obviously we could make the same argument, bless you, if we're talking about degrees. Hey, Sneezy. You sniffing some pepper this morning or something?
I was not.
No, that's just weird. It'd be a weird thing to do. Oh, you caught him? Oh. All right, so let's do just an example of applying this. So let's say we want to find all the polar coordinate points, PCP, not angel dust, you bunch of drug addicts. If you're sniffing pepper in your spare time, I don't know what else you're sniffing. These are jokes, clearly, right? Yeah, okay. I'm just making sure because there's going to be somebody listening to this recording that's like, what is going on? Yeah. You'd be like, oh, your teacher's on one today. All right. All right. So finding all the polar coordinate points. So one set of points is just the things coterminal to the given angle. Oops, I guess this is really and. The other is the ones with the opposite radius. And we flip, so we're adding pi to, and our coterminal. Now really here we should probably simplify this one. So if I add 5 pi over 6 and pi, we get 11 pi over 6. But that's the gist of it, right? All we basically did was fill stuff into our formula, right? Minimally big deal. That's pretty easy. God bless you. Uh-oh, it's catching. I don't know. All right. Same idea here, right? So what's the only difference here? Yeah, it's degrees instead of radians. Does that matter? Not really, right? We do everything the same way still. I mean, we got to use the degree version as opposed to the radian version, but whoop-de-de-de-doo! That doesn't matter a whole lot. Everybody feel okay there? Again, pretty straightforward, right? We just described what we observed earlier. You guys made the observation without a whole lot of prompting. It's a pretty obvious observation to make. And then we formalized it and it's just into a formula, and now it's just plug and chug, right? NBD. So now we have these two coordinate systems. We're comfortable plotting points in both of them. What do you suppose we need to now do? Go back and forth between the two coordinate systems. Absolutely. So we have our polar coordinate system, and we have our Cartesian, or sometimes we'll call this rectangular coordinate system, depending on who's writing the whatever. So to translate from polar coordinates to Cartesian coordinates or rectangular coordinates, I think these notes use both, like the typed out stuff that I gave you guys use both terms, or Cartesian and rectangular, so I have to throw that in here. Okay, so to go from polar to Cartesian, I need an x and a y. Everybody agree with that? Well, the x-coordinate is just going to be r times sine or cosine theta. And the y-coordinate is going to be r times sine theta. Does that look familiar? That was basically a first semester definition for sine and cosine, right? A little rearranged. Cosine was x over r, sine was y over r. Here we've just rearranged those formulas. Okay, cool. That's really easy. I love it when it's just like a formula and the formula is really not difficult, and it's something maybe I've even seen before. Woo! To go from Cartesian to rectangular, we need to get r, which, since it's the radius of a circle and the x and y lies on that circle, just the Pythagorean theorem to get an r. All right. And then the theta I'm going to write as I should say tan theta equals y over x. And I'm going to put a little asterisk there because that's not quite true, but like we'll show you how we use it. All right, let's do an example. Let's say I want to take the polar coordinate point -3, 148 degrees and convert that into rectangular coordinates. Well, x is just going to be -3 cosine 148. Y is going to be -3 sine 148. When I use my calculator to do this, the only thing I have to worry about is that I'm in degree mode. It doesn't matter whether my calculator is in function, parametric, or polar mode. That part does not matter unless you're doing some graphing stuff or using the graphing features anyways. So -3 cosine 148 is 254. And -3 sine 148 is -159. So I have the point 254, comma, -159. God bless you. Everybody should leave their seasonings at home, please. Doesn't get much easier than this, folks, right? There's a welcome change, particularly since the last couple of sections were considerably more difficult than this is right here, which I'm good with, right? Let me get a nice little break here. You think that we should have led with this? I think it's usually better to lead with the hard one, and it gives you longer to process that before the test shows up. What's brutal is when the last section is the hard one, the test is like 2 days later and you're still trying to like wrap your head around the hard thing and it's already test time. Here it's nice to like slow down a little bit and give you a chance to catch up cognitively with something that's like, okay, I can handle this. This is not a problem. All right. What if we want to go the reverse direction? So what if I want to take this and turn this into a polar point? Well, getting r is pretty easy. Now technically here, because we're talking about a polar coordinate point, this r could be positive or negative, right? We have a choice. Which one do you suppose Mr. Kulik recommends? Yeah, why would you take the negative one? That makes life just a hassle. Makes it that much harder to get your angle correct. Like, don't ever do that. You have the choice. You have the freedom to do it. But, like, why? Unless you're just like a masochist or something. All right. So if I think about the point -3, 2, that's like over here, right? So this is the angle that we're looking for. Well, relative to that angle, that side is 180, and that's alpha. So theta should be 180 minus alpha, where alpha is the tan inverse of the absolute value, y over x. Boy, does that look familiar? That's got to be the third or fourth time we've done this process, right? And applied it to different settings. If you got it figured out yet, I hope so. This is a process that we've done a bunch of times. If you haven't, this would be a great time to like finally get it. Notice on my calculator when I'm typing this in, I skipped doing the absolute value of, because I just did it in my head. And I just wrote 2/3 instead of the absolute value of negative, or 2 over -3. Everybody's good? I got 146.3-ish for theta. Or for those of you that were masochists and you wanted to do this, I don't know why, 326.3, I think. But why? I don't know. This is the one I would have reported, though. As would be the one I'd expect all of you to choose to do. Because, like, to get the 326, what did I do? I found 146 and I added 180 to it. Like, I don't know that there's an easy way to get the 346 or the 326 directly. Right? It's just like, I mean, I guess it's going to be the same alpha here. You're just doing 360 minus alpha. But, like, why, again? Like, it's too hard of thinking. Like, just let me do it the direct and easiest way. Please, for the love of Pete. There's no advantage of trying to do it the sneaky way. Or doing, I don't even know that it's sneaky. It'd be like the inconvenient way. All right, so at this point, you guys can now do 49 to 62. So I would add that on to next week's homework set. So you have now 41 through 48 and then 49 to 62. Notice if everything we did in this section was pretty easy, right? These were fast problems. It shouldn't be a big deal to get, to crank out these 14 or 15 problems or whatever that turns out to be. Assuming that you're caught up with the story problems. Now, worth pointing out to you what I promised was going to happen this week. Homework quiz. What didn't we do today?
Homework quiz.
What should you expect next class? Homework quiz. What would that homework quiz cover? Sections 10.1 and 10.2 up through 48. Up to 48. This feels like a good place to stop. We're going to stop here today.